Hi, welcome to this video. With a reference to the previous video, unit number 1, let us going to see the one more topic, external defibrillator, automatic external defibrillator. Okay, so we know why we need the defibrillator. All these things already we have discussed in the previous video. Here we are going to see the one of the type called the external defibrillator. So in this external defibrillator, an important development in the field of defibrillator has been development and successful use of smart automatic or advisory external defibrillator, this one, which are capable of accurately analyzing the ECG of the patient and making reliable shock decisions. They are designed to detect the ventricular fibrillation with a sensitivity and a specificity comparable to that of well-trained paramedics, then deliver the automatic or recommend the appropriate high energy defibrillating shock. This one is a public access defibrillators which can be placed at places like airports, train stations and other areas, using which a lay person can provide a defibrillator therapy to the affected individual. Okay, and it can analyze the electrical activity of the heart and deliver the impulses only if the arrhythmia has occurred, that is abnormality occurred. So it requires the self-adhesive electrodes and instead of handheld paddles for two reasons. The first one is ECG signal acquired from self-adhesive electrodes usually contains less noise and has a higher quality, hence it allows a faster and more accurate analysis of the ECG, and therefore it facilitates the better shock decisions. Next one is a hands-off defibrillation is a safer procedure for the operator, especially the operator has a little there is no training needed. So this is a typical diagram of this external defibrillator. It has initially thought that different self-adhesive electrode designs were needed for the defibrillation, pacing and the monitoring. Okay. So this one is a external that is a block diagram of the external defibrillator, and it is a highly sophisticated microprocessor unit that monitors the access and automatically treats the patient with life-threatening heart rhythms. It captures the ECG signals from the electrodes and runs the ECG analysis algorithm to identify the shockable rhythms and then advises the operator whether it is necessary or not, that is a defibrillation is necessary or not. So the basic defibrillator contains the usual components such as a high voltage power supply, storage capacitor, inductor and patient electrodes, and it develops an electrical charge in the capacitor to a desired voltage, creating the potential for current flow. The higher the voltage, more current can potentially flow, and this defibrillator outputs audio instructions and visual prompts to guide the operator through the defibrillation procedure. So in a typical sequence, this provides the voice prompts to instruct the user to attach the patient electrodes and starts the acquiring ECG data. If it analyzes the patient's ECG and detects the shockable rhythm, the capacitor is charged according to the energy stored in the capacitor. So already we have analyzed, that is a defibrillator analyzer, that self it is analyzed in the previous video. Then following by the instructions from this processor, the operator presses the shock button to deliver the high voltage pulse. High voltage pulse. So the current begins flowing through the body to the depolarize most of the heart cells, which often re-establishes the coordinated contractions and the normal rhythm. So the amount of flowing current is determined by the capacitor and the body impedance. The front end signals of the defibrillator come from the ECG electrode placed on the patient, which records the instrumentation amplifier. This one instrumentation amplifier, very small amplitude, that is less than 10 millivolt. Okay, so these are the informations regarding this external defibrillator. Another classification is internal defibrillator. The use of automatic implantable defibrillator is recommended for the patients who are at a high risk for ventricular fibrillation, and this is a small matchbox sized. So this one small matchbox sized device that can be implanted in the body, that is in the chest or in the abdomen. It can constantly monitor the heart rhythms and deliver the necessary electrical impulse before the disrupted rhythms translate to cardiac arrest. So this one is our simple implantable defibrillator in the chest. A modern implantable defibrillator is an implanted computer which shows the recordings of the patient heart signals and collects the extensive therapy history and the diagnostic data files to aid the physician and individualizing device behavior for each patient. Less than 70 ccs in volume and with over 30 million transistors, these implantable devices draw less than 20 microamps during the years of constant monitoring of the patient's cardiac status. So this is a small information regarding this implantable defibrillator. So an implantable defibrillator continuously monitors the patient's heart rhythm. If the device detects a defibrillation, the capacitor within the device are charged up to 750 volts. These are all the informations already discussed in the previous video. 750 volt. The capacitor are then discharged to the heart, which mostly represents a residual load of 50 ohms and brings the heart into the normal rhythm. And another thing, the results reports that appropriate biphasic waveforms and monophasic waveforms are more efficient and probably safer than the monophasic waveforms and produce a successful defibrillation at lower energies. And this one, a small capacitor must be charged to a higher voltage to store the recovered energy. So the discharge current pulse duration is approximately 2.5. It is in the range of 2.5 to 3.5 milliseconds for most defibrillators and doesn't increase very much with the patient impedance. So it is based on the several research. A biphasic truncated exponential waveform has become the standard waveform. This one, standard waveform. So let us move on to the block diagram of this implantable defibrillator. So the basic components of implantable defibrillator, it contains a battery, capacitor to store the and deliver the charges, and the microprocessor based, this one, and integrated circuits for ECG sensing data capture, storage and control of therapy delivery. A header to connect endocardial leads used for sensing, pacing and the defibrillation. So all these components together are called pulse generator and are cased in a titanium can. So the major subsystems of the implanted pulse generator are shown in this diagram. So it has a microprocessor which controls the overall system. An 8-bit device is sufficient for the most systems. ROM provides a non-volatile memory for a system startup task and some program space, whereas RAM is required for storage operating parameters and storage of ECG data. So the system control part includes the support circuitry for the microprocessor like telemetry interface, typically implemented with universal asynchronous receiver, that is UART interface, and general purpose timers. And the power supply usually to the circuit comes from lithium silver vanadium oxide batteries, and whereas digital circuits operate from the 3 volt, whereas analog circuit typically requires a precision nanoamps current source of input. And high power circuit, this one converts the 3 to 6 volt battery voltage to the 750 volt necessary for the defibrillation pulse, store the energy in the high voltage capacitors for timed delivery, and finally switch the high voltage to cardiac tissue or discharge the high voltage internally if the cardiac arrhythmia self terminates. So these major components of these circuits are the battery, DC to DC converter, output storage capacitors and high power output switches. Usually DC to DC converters used to convert 6 volt battery to the 750 volt is of classical configuration. They are operated at a high frequency in the range of, that is 30 to 60 kilohertz. as a practical to facilitate the use of smallest possible core. The storage capacitors in this circuit, typically aluminum electrolytics, because of high volumetric efficiency and working voltage required. Proper sensing of electrical activity in the heart requires precise sensing and discrimination. This one, sense amplifier, and the discrimination of each components that comprise the intracardiac signal to differentiate the tachycardia and ventricular fibrillation. Also, the sense amplifier must also be immune to both physiological and external sources of interference. So from the electrical standpoint, the sense amplifier must be able to operate properly over a range of from 30 to in excess of 360 bpm. So the heart signals of interest lie in the range of 100 microvolt to 20 millivolt, and as a result must be amplified prior to be processed. If the signal being sensed drops suddenly in amplitude, which is a common during the fibrillation, so the automatic gain control, that is in this amplifier circuit, automatic gain control circuit increases as gain so that the fibrillation signal continues to use a system dynamic range. So the dynamic threshold circuit may then be used to sense the R waves for R fibrillation. So this sensing circuit is active throughout the entire life of implantable defibrillator to minimizing the power consumption of these circuits, and it is a beneficial impact on the device for the lifelong. So depending on the number of leads, the placement into the cardiac chambers, so it can be classified into single chamber, dual chamber and biventricular. So the single chamber, dual chamber and biventricular. So in the single chamber, these have a single lead that is placed in the right ventricle. So in the heart, the right ventricle, and provide the antibradycardia and anti-tachycardia therapies. Whereas in the dual chamber, they have two leads that are placed in the right atrium and the right ventricle. These units can provide the antibradycardia pacing through the right atrium and ventricle, also provide the anti-tachycardia therapies, cardioversion and defibrillation through the right ventricle only. So in the biventricular, these devices have three leads, of which one is placed in the right atrium and the remaining two are placed in left and right ventricles each. So in addition to the functions provided by the dual chamber, and these provides a capable of synchronized pacing to the left and the right ventricles, which is useful for individual at a risk high heart failure. Once again, these are all the reference. So thank you.